Okay, so we're going to start the next section having to do with directional derivatives and gradients. So we're going to start out with a function, an ordinary function of two variables. Oops. So f as a function of x and y. And so here's the graph, right? It's just a surface sitting above the xy plane. It could be below the xy plane if z is negative, but let's suppose that z here is positive, right, for at least these x's and y's here. All right, so now I'm going to take a particular point in the xy plane, say right down here. So this is xy, and then z is 0. And then on the surface, right, this is the point xyz, right there. So if you take a line on the xy plane in the x direction, right, so effectively this is just the line y equals whatever, right? So y equals y, essentially, right? So looking at it from the xy plane, right? It's parallel to the x-axis, right? So I didn't give it a specific y. I just called it y. So yeah, I should have called it like a and b. All right, so maybe let's do that then. So instead of calling it x and y, right, or I could use x0, y0, but I'll just use a and b. And then going up to the surface here. Right, I don't need all that. So this will be a, b, and c, I guess. Right. So this is, right, these are just specific x, y, and z values. Right. So now we can take this horizontal line, and on the surface, when you project it upward to the surface, you get a curve like this. Right. So each point on the red line below gets mapped up to the curve on the surface. Makes sense? Right. And you can also do this horizontally, or in this case vertically. I can get the right line here. Right. So if you project this up to the surface, you'll get another curve. Something like that. Right. And so, just as a quick review, remember we talked about the partial derivative of z with respect to x, or f with a subscript x, right? And so that's just the slope of the tangent line in the x direction as x is changing, right? So if we plug in the particular point AB here, right, then the slope, the partial derivative will be the slope of this line here in the x direction. So it looks like it's sloping downward, so it could be negative. That could be a perspective issue, but right. So the slope of this green line here is the partial derivative of f with respect to x, right? And you can play the same game with respect to y, right? At the same point, now as y is changing, right, you get the slope of the tangent line. Pretend it's a straight line. It's very hard to draw a tangent line here because it's pretty straight anyways. So the slope of this line here will be f subscript y. Again, plugging in the a and the b. And maybe I should have, right, So at that specific point, you get a specific value, right? All right, so that's just reviews the partial derivatives. But then you might wonder, well, what's so special about the x direction or the y direction, right? What if I'm at this point AB and I want the slope in some other direction? Let's say this direction, right? So I go up to the surface, and on the surface I get a curve, something like this, right? So now, if I go up to the surface, I get a tangent line with this slope. So how could I find the slope of that line in a particular direction that's not the x direction or the y direction? Right? So that's the idea of the directional derivative. It could be a derivative in any direction, not just the x direction or the y direction. Okay. So how do we do that? So first of all, how do we establish a direction, in the xy plane? So there's several ways to do that. After all, this orange line down here, it's a line in both directions. This orange line here is a line in the xy plane. So we could describe that line parametrically, We can say that x is just x0 plus, not x0, sorry, a, So a plus, well, then we used an a here too. So, all right, so let's do it this way then, Let's pick out the direction as an angle with respect to the x-axis, And let's just call it theta. So yes, I can pick out a direction just by using the angle theta here. So I shouldn't have used a and b. That's my mistake, but so anyways, the parametric equation of this line you can write as x equals a plus t times cosine theta. And then y will be b plus t sine theta. So that would describe the line parametrically, If you want the direction as a vector, let's say you have a vector in this direction, and let's make it a unit vector, u. You can just use cosine theta times I plus sine of theta times j. So that's my unit vector u. Okay, so now what's the slope of the red line here? This red line here. Well, let's pick 2 points on that line, One of the points should just be that point right there. I'm trying to highlight that point. So the point where all these curves intersect, So again, that point is what I'm calling A, B, and C. Maybe I shouldn't have called it that, but it's too late now. So we'll call it A, B, and C, where right below it is the point A, B, and then Z is 0 down there, And one other point, I'm running out of colors here, but how about this point way down here? Yeah. So this point on the orange curve up here. And so if you go down, you'll end up at a point on the orange line in the xy plane. And so what are the coordinates of this point? Well, so we might as well use one of these x's and y's. So it's just some value of t. T is essentially the distance between those 2 points. So yeah, this point will have coordinates x, y, 0, where x and y are, right, a plus t cosine theta and b plus t sine theta. I just don't have space to squeeze all that in here. B plus t sine theta. Okay, I think I just made it. Right. So, yeah, so that's that point there. And so if we take not the tangent line, but a secant line through those 2 points, obviously it won't be the same as the red line, but we can take the limit, right, as essentially t goes to 0 here. As t goes to 0, you approach the point AB. Okay, so I feel like I should do this in red, but well, for now it's this blue line here, right? So the slope of the secant line, right, passing through two points. One of them is A, B, and C. And the other is, I'll write it out explicitly, a plus t cosine theta, b plus t sine theta, and then f of that point there, right? So I'll just call it x and y, right? Where x, right, this is my x, this is my y. Yeah, so this is x, this is y. Okay, so to get that slope, you do the usual thing, right? Rise over run. So here's the rise. Oops, sorry. So I'm really running out of colors here, right? So this is the rise, and then this is the run. Right, the run is just t. The rise is the difference in the z-coordinates, right? Okay, so that slope is just going to be f of, and let's spell it all out, a plus t cosine theta, b plus t sine theta, minus, well, right, f of ab, which I've been calling c here. Right, so c is just f of a and b, and then divided by t. Right, so that's the slope of this blue line, this light blue line here. And then to get the slope of the tangent line, we'll do it this way, right? So the slope of the tangent line at the point ABC will just be the limit, right, as t goes to 0 of f of a plus t cosine theta, b plus t sine theta, minus f of ab all over t. Okay. So the slope of that tangent line, that red line, that big red line here, that's supposed to be the tangent line. This is what we call the directional derivative of the function f of xy, right? So that's the entire function, at the particular point AB, right? But then we also have to spell out the direction, right? What direction are we going in? Well, we can use theta, right? Or we can use the unit vector u, right? So we're going to use the unit vector. So in the direction of the unit vector u, which has components, right, cosine theta, sine theta. And that's what makes it a unit vector is the usual, right, cosine squared plus sine squared equals 1. So that's the norm of the vector u. Remember that? Right. So that picks out a direction, right, either the theta or the unit vector u. Right. So there you go, right? This is the definition of the directional derivative. Right. And it is the slope of the red tangent line. right? Right. And in particular, right, depending on the direction, let's suppose theta is 0, right? So if theta equals 0, in which case u is just the vector I, right, in the x direction, then the directional derivative, right, if you calculate this limit here, the directional derivative will just be the usual partial derivative with respect to x, because it's in the x direction, right? It's this little red line in the xy plane, not to be confused with the red line that we're finding the slope of the tangent line, right? And if theta is, say, pi over 2, 90 degrees, then the unit vector u is just the vector j, in which case the directional derivative is just the y partial of z. Right. Right. At AB, of course. We should have mentioned that. So at that particular point AB, right? So essentially the green line here is the x partial. This, I don't know, pink line here is the y partial, and then somewhere in between is this red line, which is the directional derivative in the direction of u, right? Which is some combination of I and j, right? You think of this as a linear combination of I and j, right? Okay, so yes, so if this limit exists, then you get a directional derivative, right? If the limit does not exist, well, then the directional derivative will not exist at that point, right? And you can guess when that happens, right? If you have a surface with some sort of a crease in it, like this, right? Or if you have, say, the peak of a cone, at that point, right, there's no directional derivative, right? Because the function would not be differentiable there, right? So sure, it's right. If this limit fails to exist, then there's no directional derivative. But for most of the examples we're going to look at, the limit will exist, and you can calculate the directional derivative, right? But before we do that, because again, this is a very unwieldy way to find the directional derivative, and in fact, we're not going to use that definition. It's just not very practical. But it does give you the intuitive idea that, right, what you're looking for is essentially rise over run. Right. This is the rise, this is the run, and so it is the slope of the tangent line in a particular direction, right? And so that gives you the idea. Hopefully it's intuitive, and it's also just the definition. And if the picture is confusing at this point, let's just flip it, and let's say this orange line down here is the direction we're going in, right? So let's do the orange line horizontally, and then above it you have the surface, which at this point might look like a curve, but remember it is a surface in space. And we're looking for the derivative at a particular point, and that gives us the red line here, which is the same red line as above. I'm just changing the perspective a little bit. So we're looking for the slope of this red line here, right, at this point. This is AB0, and this is ABC, right, where C is just f of AB. So we moved a little bit in this direction, right, some distance t, to this point here, which became, I hate writing it down again, but a plus t cosine theta and b plus t sine theta. And then, oh, and z is 0, sorry. And then when you move up, you get to this point on the curve, and we connected those points with a blue line. I already used blue. I'll use a different shade of blue. So there we go, right? So this is the secant line, so that would be the slope of this blue line here before we take the limit as t goes to 0. So, right, as t goes to 0, right, this point right here moves closer and closer and closer to the point ABC, to the point where the secant line is almost indistinguishable from the tangent line. And so, right, in the limit, as this t approaches 0, this point gets closer and closer to the original A, B, and C, and then you have the slope of the tangent line. So that's the, right, more of a Calc 1 type calculation at that point, right? So that's the idea, right? All right, so now we have a theorem that'll allow us more practically to calculate these directional derivatives without having to resort to this very awkward definition. Right, and maybe before we give you that theorem, what's the notation for the directional derivative? So it's just a capital D in the direction of u of the function f evaluated at a and b. So an easier way to calculate the directional derivative is as follows. And here it is, right? So this is theorem 13.9 in the 11th edition of the book. If f is differentiable, right? And again, in the sense from 13.4 when we talked about when is a function differentiable, right? It's when the tangent line exists in every direction. Then the directional derivative of that function f as a function of x and y in the direction of u, and u is the unit vector in the theta direction, right, is given by, so we have the capital D for derivative in the direction of u of the function f of x, y. So it's just the partial derivative of f with respect to x times the cosine theta plus the partial derivative of f with respect to y times the sine of theta. So yes, a much more practical, much easier way to calculate the directional derivative than to have to go through and calculate this limit up here. Right? So yep, that's probably the easiest way to do it, right? Because by now you know how to calculate the directional derivatives, right? And if you're given theta, then you just plug in the sine and cosine of theta. If you're given the vector u, right, in component form, right, then of course the x component is, right, the cosine of theta, and the y component is the sine of theta. So you can easily figure out theta by just taking the inverse sine or cosine, or tangent if you want to do both, right? Okay. So, right, so do you buy this? Is this likely? Maybe I should prove it. Okay, let's prove it. I'll try to make it fast, right? So the directional derivative, right, is basically exists at each point. And each point, x, y, could give you a different directional derivative. As you change your point, right, even if you keep the same direction, you might not have the same slope, right? So different points will have different slopes, even if you're going in the same direction, right? Even with the same theta. So let's fix, right, a specific point, and right, let's not call it a and b. Let's call it x naught and y naught, right? Then your unit vector u, right? Well, it's still, you can still use cosine theta, sine theta. I guess what I want are the parametric equations of the line. Remember this orange line down here? So, right. So then, any given point on that line will have an x-coordinate of x naught, x0 plus t cosine theta, and y will be y naught plus t sine theta. Right. Okay. So now what we want to do is form a new function called g of t, and it's just going to be the function f right, evaluated at x of t and y of t, right? Remember, right, x and y now will be restricted to the point right, on that orange line. So here's the xy plane, and then here's the orange line, right? So we fixed a point x0 and y0 in the xy plane, and then to get to any other point, right, on that line, you only need to specify how far away you're going, right? You have to specify t. Right. So that gives you a point on that line, and now based on that, we have a function that only depends on t. Right. So g is a function of, well, implicitly it's a function of x and y, but explicitly it's just a function of t. So what are we going to do with this? We're going to take its derivative, of course. G prime of t, right? So this is a Calc 1 derivative, right? It's a function of one variable, and you're taking the ordinary derivative. However, f, of course, is a function of two variables, x and y. So for that, we need the chain rule, right? We need to take the derivative of f with respect to x, right, times the derivative of x with respect to t, plus the derivative of f with respect to y, times the derivative of y with respect to t. With respect to t. What am I doing here? Right. So that's the chain rule from the last section. And we can maybe rewrite this in terms of the subscript x, right? And again, this is at some particular point here, xy, times x prime of t, right? Same thing as dx over dt, plus, and then the partial of f with respect to y, f subscript y, at the point xy, times y prime of t. Okay? Right. So now, what's x prime of t? Well, what's x, right? X is defined this way. Remember, x0 is a fixed number. It's just a number. And theta is a fixed number. So this is a function of t. So if you take the derivative with respect to t, you just get 0 plus cosine theta. And for y prime of t, of course, you just get sine of theta, right? Take the derivative of this with respect to t, right? And you get sine theta. Sine theta is the constant multiplying t. Right? So there you go. Now you get f subscript x. That's the partial of f with respect to x at x and y times the cosine of theta, right? Plus the partial of f with respect to y of xy times the sine of theta. Right. Now it looks like we're done. It looks like that's what we wanted to show, but technically we wanted to show this, right, at a particular point, at x0, y0, at this point here. Okay, so in order to do that, we have one more step here, right? What we really need is to take the derivative of g at t equals 0. Right? At t equals 0. So what happens at t equals 0? Well, remember, x is x0 plus t cosine theta. If t is 0, then x is just x0, right? And y is just y0. So now we get f subscript x, so the x partial of f at x0, y0, right, times the cosine of theta, plus the y partial of f at x0, y0 times the sine of theta. Right? And that's what we wanted to show, that the directional derivative in the direction of u, right, of the function f evaluated at a specific point, x0, y0, is given by what I just wrote up here. So I guess I have to copy it down again. x0, y0, right, times sine theta. So that is the formula for the directional derivative of a function f at a given point in a given direction. The given point is x0, y0, right? We fixed that point right there. And the given direction is based on the unit vector u, which I didn't write down, but it's also the angle theta. Right? So it's this angle here in the xy plane. Got it? All right, so I think that does it. That's right. So yeah, now we can do an example, and again, we'll calculate the directional derivative using this theorem rather than using this awkward definition involving limits, right? And again, you should know how to calculate a limit, but in all but very simple cases, it tends to be very, not very simple to do. Whereas just calculating partial derivatives, by now you're used to that, I think. Okay, so we have a function of two variables, right? And this is, well, it's just some quadric surface. In fact, I'm pretty sure it's a paraboloid, right? In a non-obvious way, because you get this combination of x times y. So it's effectively like a rotated paraboloid. But it doesn't matter. It's just some surface. And we want to find the directional derivative of this function at the point x equals 3, y equals 1 in these various directions, right? And there's 8 of them. So it looks like we have a lot of work to do. But it's really a lot, right? Because there's eight of these we have to figure out. But it's not that bad. So we're going to use the following definition. Sorry, not the definition, the theorem, which says that the directional derivative is just the partial derivative of f with respect to x at the point xy, right, times the cosine of theta, plus the y partial of f at that point times the sine of theta. And we have just different thetas, so different sines and cosines, right? And in particular, we're doing this only at one specific point, right? The point 3, 1. Oh, before we do that, maybe we should calculate the partial derivatives, right? So what's the x partial derivative? So 2x plus 4y. Right? And then the y partial is going to be, let's see, 4x plus 6y. Okay, so those are the two partial derivatives in the x and y directions, right? But remember, we're going to just plug in the 3 and the 1. So 2 times 3 plus 4 times 1 is 10. And then for the y partial, you plug in the same 3 and 1. You get 4 times 3 plus 6 times 1. 12 plus 6 is 18. Right? So back to the picture here, you're just going to get 10 times cosine theta plus 18 times sine theta. Right? Now we just plug in the different thetas, right? So for part A, theta is pi over 6. Well, right, so the cosine, and I don't know why I'm using u here. Let's use theta equals pi over 6 of the function at this point. So you just get 10 times the cosine of pi over 6 plus 18 times the sine of pi over 6. Right? So cosine of pi over 6 is square root of 3 over 2. So 5 times the square root of 3. And then sine of pi over 6 is 1/2, so that's just 9. So there you go. There's the directional derivative in the direction of theta is equal to essentially 30 degrees, right? Pi over 6. Right, and so maybe for reference, it's approximately 17.66, right, which is pretty steep, right? That's a pretty steep line, right? It's the slope of the tangent line, right? So, all right, part B, theta is 2 pi over 3. So now the directional derivative in the direction of 2 pi over 3 at the same point, 3, 1. Well, okay, so cosine of 2 pi over 3 is negative 1/2. So that's going to be negative 5. And then the sine of 2 pi over 3 is still square root of 3 over 2. So 9 square root of 3. Yeah, 18 over 2 is 9. 9 times square root of 3. So I get about 10.59. Right, still pretty steep. There's the exact and there's the approximate. All right, what about pi over 2? Well, cosine of pi over 2 is 0, right? And then sine of pi over 2 is 1. So you just get 18. Right? And notice that's just the y partial derivative, right? So this is the same thing as the partial of y with respect to, sorry, the y partial of f, right? The partial of f with respect to y at the point 3, 1. Right? So yeah, you're just picking out the y direction here. So no surprise that the directional derivative in the y direction is the y partial derivative of f. Right? And then d, theta equals 0. So, right, so that's in the x direction. I should say theta equals 0 here. So you're just going to get the x partial derivative, right? You're going to get 10 times 1 plus 18 times 0. So you're going to get 10. And so this is just the x partial derivative at the point 3, 1. No surprise there. Right? All right, part E, we want 7 pi over 6, which is just the polar opposite of pi over 6, right? You add pi to pi over 6, you get 7 pi over 6. Right, so let's see. Cosine of 7 pi over 6 is negative square root of 3 over 2. Right, so that's going to be negative 5 square root of 3. Sorry. And then the sine of 7 pi over 6 is just negative 1/2. So that's negative 9. So, yep, this is just going to be approximately negative 17.66. There's the exact, there's the approximate. Notice something? Right? So if you look way back up here where you have pi over 6 rather than 7 pi over 6, we just got a positive 17.66 instead of a negative 17.66. Right? Coincidence? So think about what you're doing, right? If this is, let's say this is the direction for theta equals pi over 6. And I know this is going to be a very steep graph, but it's going to be something like this. I can go even steeper than that. So there's the function in that direction. And at the point, right, 3, 1, you go up, right? In this direction, right, rise over run is a positive 17.66. So notice where 7 pi over 6 points in this direction, in the opposite direction. So now, rise over run is going to be negative, right? You're going in the negative direction, you're going to get a negative slope because you're going downward right, instead of upward. Yeah, so, right, remember, this is in 3 dimensions now. This is a 2-dimensional surface sitting in 3-dimensional space, right? So yeah, in the polar opposite direction, you get a negative slope because you're going down instead of up. Yeah, be careful, because in Calc 1, we did not make that distinction, did we? If you have a curve, a 1-dimensional curve, right? Say f of x, and you picked a certain point on that curve, a specific value of x, say x0, and you found the derivative, right? Let's say it was this, then this is going to be, rise over run will be a positive, right? So this would be a positive number. Okay? We never really said, because, right, look, this is in the x direction, right? We never mentioned, oh, the possibility of going in the negative x direction, because that's just in the opposite direction. So yeah, if you're going left to right, you're going up the hill. If you're going right to left, you're going down the hill, which means you're going, right, where the slope is negative instead of positive. So yeah, in Calc 1, we never made that distinction, right? We're always going to the right in the positive direction. But now we're allowing ourselves to go in the negative direction. And, right, so you should just get the opposite slope of going in the positive direction. Right? And so notice that F, G, and H are all just the opposite directions of B, C, and D. Right? 5 pi over 3 is 2 pi over 3 plus pi. Right? 3 pi over 2 is pi over 2 plus pi. And obviously pi is 0 plus pi. So when you add pi, you're just going halfway around. Right? So we can do F, G, and H very quickly. For F, you're just going to get the opposite of B. So it's going to be 5 minus 9 squared of 3, which will be about negative 10.59, right? 0.59. And for part G, you're going to get the opposite of C. This is C here. You're going to get negative 18, right? And then for H, you're just going to get negative 10. Okay, so you just get the opposite values of going in the positive direction. Make sense? Yeah, so we don't, I mean, you can calculate these if you want by using the formula here. But effectively, when you add pi, you're going halfway around, you switch from a positive cosine to a negative cosine, right? Or a positive sign to a negative sign. Okay. So yeah, this is what I wanted to illustrate with this example, is that these angles here are just in the opposite direction of these angles, and so you should just get the negative of the directional derivative. Right. So the directional derivative can obviously be negative or positive, right? Or 0, right? And if you're 0, then your tangent line is just horizontal, right? So that can happen too. So I hope this helps. This is a pretty typical example of calculating the directional derivative. Okay, so maybe we'll do one more example of a directional derivative. So here we're given the function f of xy is just x squared times the natural log of y over x. We want to find the directional derivative of that function at the point 1, 2, right, in the direction of u, where u is the vector 4, negative 3. So the x component is 4, the y component is negative 3. Okay, well, again, not using the definition, using the limit as t goes to 0, we'll once again use this formula here. If I can remember it, right? So it's the x partial of f at the point xy times the cosine of theta plus the y partial of f times the sine of theta. Okay. Now, there's one important problem here. There's one issue. This is a trick question. Right? So I'm making it out to be easier than it really is. So here's the issue, right? Back when we defined u as the direction, u just points in the particular direction, right? It just picks out a direction that you want to go in, right, in the xy plane. Okay. And again, all these vectors have, different thetas. So you can also use theta, which is what the formula calls for. However, right, the problem is that the u here might look something like this. Right? Oh, for -3. Sorry, wrong direction. Something like this, right? So what's the problem? It's not a unit vector. Right? It doesn't have norm 1. Its magnitude is not 1. So I shouldn't have called it u. I should have called it v. And we can easily change it to a unit vector by just dividing by its magnitude, right? Which in this case is just 5. So we're going to get the vector 4 over 5, -3 over 5. Okay? Right. So if we do that, already we now know the cosine of theta is 4 over 5, and the sine of theta is -3 over 5, because this is still u. Right? So yeah, you have to be careful. You can't say, right, cosine of theta equals 4, and sine of theta equals -3. That's nonsense, right? Cosine and sine have a range from -1 to 1. So the cosine can't be anything bigger than 1. It can't be less than -1. So yeah, you might have been tempted to do that, but you would have gotten the wrong answer, right? Right. So cosine of theta has to be less than 1. So, right, so 4/5, 0.8 is less than 1. And it has to be bigger than -1, right? Like -3/5. So yeah, if they don't give you a unit vector, first thing you have to do is to normalize it, divide by its norm, and write it as a unit vector with magnitude 1. Right. So now you can check that the magnitude of this is indeed 1. I can write a 1 there. Yeah. Okay. So really the only issue here now is calculating the partial derivatives. So the partial derivative, we're looking 6 here. So the partial derivative of z with respect to x, or f subscript x. So yeah, we need the product rule. Actually, yeah, and then we might need the quotient rule inside here. But remember that y is a constant in this case. So what I'm going to do is simplify this a little bit. You can also write this as x squared times the log of y minus x squared times the log of x. I find that might make it a little bit easier. So now the x partial derivative will just be 2x times the natural log of y minus, and now we really do need the product rule here. So first times the derivative of the second is just x, plus second times the derivative of the first. Right, I think that's it. So we end up with 2x times log y minus log x. So that's just y over x again. And then just minus x, I think. So I think that's it. Oh, and we're only going to plug in, right, 1 and 2. So if x is 1, you get 2. Natural log of 2 over 1 minus 1. So, yep, 2 log 2 minus 1. Right. And now we need the y partial. I need that up here. So the y partial of z, fy, right? So remember, x is a constant, so the derivative of log y is just 1 over y, so this is just x squared over y minus 0. So, yep, just x squared over y. And now if we plug in the 1 and the 2, we just get 1 squared over 2, or 1/2. Okay, now for the directional derivative, what are we going to get? So the directional derivative in the direction of u, and again, it's this u here, the unit vector, right, at the point 1, 2, is going to be, so the x partial was this number here, 2 log 2 minus 1, times the cosine of theta, which is 4 over 5, plus, and then 1/2 times the sine of theta, which is negative 3 over 5. And that's it. I think we can simplify this a little. What do we get? We get 8 log 2 over 5, right, minus 4/5, and then minus 3/10. So 8 log 2 over 5, and then minus 8 minus 3, minus 11 over 10. Or if you prefer, 16 log 2 minus 11 all over 10. And I'm pretty sure that's a positive number. Again, it could be negative. Yep, it's a very small number though. This is approximately 0.009. So, yep, not even a 1% slope. So a pretty small number. Right? So the slope of the tangent line is pretty small. So it's not increasing very much at this particular point in that particular direction. Of course, if we picked a different direction, we might get a very different answer, right? And if we picked a different point, instead of 1, 2, we picked, 3, 7, again, we would get a very different answer, right? I presume. Yep, so that's it for this example. And so, again, this is not that hard once you get used to this calculating directional derivatives. However, there's another way to think of it, right? If you don't want to deal with the sine and cosine of some angle, in fact, we never found the angle here, right? We never did find theta. We just used the sine of theta and the cosine of theta. We used, right, these here. Right? So, yeah, if we wanted to find, say the angle itself, you would have to take, the arc cosine of 4/5, which I guess I can do. It's 36.87 degrees. However, I think we want y to be negative, right? So we want this angle. So I think it's going to be negative 36.87 degrees. Or if you prefer a positive angle instead, just add 360 and you get 390. Oh, I'm sorry. I forgot to make it negative. Plus 360, 323.13. Okay. The point is, though, we never had to find that angle. And so if you don't want to bother with this sine and cosine, there's a useful device that we're going to use, and it's just based on the two partial derivatives, right? Okay, so we're going to define a vector whose components will be the partial derivatives of the function. So we're given a function, z as a function of x and y. Let's suppose it's a differentiable function, right? Then we're going to define the gradient of that function, of f, to be the following vector, right? So you can spell out grad for gradient as an abbreviation to gradient, or you can use this symbol here, right? This upside down triangle with the little vector on top, right? Because it is a vector, right? And it's just the vector with these two components, right? The x component is the x partial derivative, and the y component is the y partial derivative, right? And you can write it this way too. It's the same thing, just written with a different notation, right? But I have to emphasize it's a vector, right? Right? So it has two components. Okay, so this little symbol here, right, is sometimes called the del symbol, right? So it's an upside down delta, right? So it's just del of some function f, right? So the del itself, without anything after it, basically is the following vector, right? The I component of the vector is the partial with respect to x, and then the j component is the partial with respect to y. Right. So if you put an f after it, a function that comes after it, then the I component will be the partial of f with respect to x, and then the j component will be the partial of f with respect to y. You know, whether you put the I and j in front or in back doesn't matter. It's traditional to put it in back. So why did I put it in front here? Because I don't want to give you the impression that if I put it in the back that you're taking the derivative of the vector I, right? You're not taking the derivative of anything here, right? It's just it's a derivative operator, right? So the gradient is a derivative operator, right? So this is nothing new, right? Back in Calc 1, right, you wrote this symbol, right, to represent the derivative with respect to x. But the derivative of what, right? We don't know yet. It's just the derivative. So if you want to write, let's say, the derivative of a function, derivative of, let's say, g of x, then you would write the derivative of g of x. Or, you know, more likely you'd write it g prime of x, but you can also write it this way too, right? So this symbol just means take the derivative of, you know, whatever comes after it, right? Whatever function you put after it. So likewise, this del operator, this derivative operator, just says, right, take the gradient of whatever function comes after that symbol, after the gradient symbol, right, or the del symbol, right? Yeah. So the symbol itself, if you're looking for it, you know, it's not going to be on your keyboard, but if you're using LaTeX, of course, I think it's the nabla symbol. Someone in my last class says, you know, nabla español, but it's, yeah, nabla instead of H for habla. Anyways, yeah, so I'll just call it the gradient symbol, right? You can call it del, you can call it nabla. It's just gradient, right? So let's do some examples. Oh, I'm out of space. So here's the definition of the gradient, and now we'll do some examples. Okay, so this function should look familiar. X squared plus 4xy plus 3y squared. We use that to calculate the directional derivative. But now we just want to calculate the gradient. I calculate the gradient of this function, right? And in fact, it could just say, you know, the question could just say, find the gradient of f, right? So you should know what this symbol means, right? Yeah, I mean, it's on your formula sheet, but really it's not that hard to remember, as long as you remember it's just the vector with components, right? Partial of f with respect to x, and partial of f with respect to y. Right, so the y partial is the y component, the x partial is the x component. Not hard to remember, I don't think. And in fact, we already took their partial derivatives when we did the directional derivative, right? So let's just do it again, right? The x partial, you just get 2x plus 4y, right? So that's the I component. Plus, right now with respect to y, you get 4x plus 6y. And that's the j component, the y component, right? So there you go. That's the answer. Nothing else to do there. Right. Now, this might look like a weird vector because it's a vector that depends on x and y. Okay, so to make this a little more concrete, why don't we plug in some points? Right? What if I plug in 0, 0? Right? In other words, x equals 0, y equals 0. Well, then I just get the vector 0i plus 0j, otherwise known as the 0 vector. Right? It's still a vector, but it's just a vector with 0 magnitude and 0 direction. Right? But suppose I plug in the point, what was it, 3, 1? Yeah, 3, 1, which we did earlier. Right? So now we get 2 times 3, right, plus 4 times 1. And that's in the I direction. And then 4 times 3 plus 6 times 1 in the j direction. Right? So this is just the vector 10i plus 18j. Or if you prefer, right, 10, 18 in component form. Like I say, I'm not picky here. Right? So yeah, you can also write the 0 vector as just 0, 0. Either way. Okay, so yeah, that 10 and 18, that should look awfully familiar, right? Those were the partial derivatives that we used when we calculated the directional derivative, right? At that point, we just plugged in different thetas, you know, different cosine theta, sine theta. Right? Right. So let's maybe pick one other point here. How about the point -5, 7? So again, we get 2 times -5, right, plus 4 times 7, and that's in the I direction. Right? And then in the j direction, in the y direction, we get 4 times -5 plus 6 times 7. Okay, so this is 28 minus 10, so now this is 18. And then we get, let's see, 42 minus 20 is 22. Wait, 42 minus 20, yeah, 22. Right? So 18i plus 22j, or just 1822. Okay. Right. So yeah, at each point in the xy plane, you get a different vector. Right. So that's kind of new here, right? This is an example of what's called a vector field. Remember, at the beginning of this chapter, we talked about scalar fields where each point has a different number, right? Like temperature has a different value at each point in space. But now, again, we're just talking about the xy plane here, right? Because these are vectors with 2 components. There's no z component to any of these. Right? But the way to think of it is that each point will have a vector, right? Now, it might be the 0 vector at the origin, right? And then at the point 3, 1, we have the vector 10, 18, so that might point something like this. At the point -5, 7, which is way up here somewhere, you'll get a different vector. Well, it's still something like this. You know, they look parallel, but they're not, right? So at this point, you might get this vector. At this point, you might get this vector. At this point, you might get this vector, right? So each point has a different vector. Right? It should be a continuous vector field here, right? At this point, you might get, you know, this vector. At this point, you might get a very small vector. At this point, you might get a very long vector, right? So each point has a different vector. This is an example of a vector field. Right. So, right, by plugging in this specific point here, you get a very specific vector. If you plug in a specific point here, you get a specific vector. But it could be a different vector depending on what point you're looking at, right? Okay. So the gradient is one example of a vector field. And we'll see vector fields again when we get to chapter 15. Right. So a vector field does not have to be a gradient. But a gradient is definitely one example of a vector field. Okay, so let's maybe... before we do another example, so the point of using the gradient here is just to recast Theorem 13.9 in a different light, right? So remember, we can calculate the directional derivative of a function in the direction u as the partial with respect to x times cosine theta plus the partial with respect to y of the function f, I should say, times the sine of theta. Okay, so we can write this in a somewhat more convenient format. If you don't want to deal with theta, and you just want to deal with the direction u as a vector, you can write this as the gradient of the function f, again, at the point xy, and then take the dot product of this vector with the vector u. Okay. So this is yet another way to calculate the directional derivative, right? And just to make sure that this makes sense, let's untangle this, right? What is the gradient of f? It's the gradient, it's a vector whose components are fx and fy, right? Are the two partial derivatives. Right. Dot product with u. Well, what are the components of u? Well, if u is a unit vector, the components are cosine theta and sine theta. Right. So now how do you take the dot product? You multiply these, and then you add it to this product here, right? So you get the x partial of f at the point xy times the cosine of theta, plus the y partial of f at the point xy times the sine of theta. But of course, that's exactly what we already have. That was Theorem 13.9. Right? So, yeah, I prefer to write it using the gradient dot product with u. Right? But you can also use it using these partial derivatives. It's essentially the same thing. You're just calculating it in a slightly different way using angles instead of vectors. Right. Okay, and so let's not get confused here, right? This is not the gradient, right? This is the directional derivative, right? So don't get confused between gradient and directional derivative, right? This is the directional derivative. Right? It involves the gradient. The gradient is one of the vectors that you're using for the dot product. But the gradient itself is not the directional derivative. Okay, so just to be clear, the directional derivative, right, is a scalar. It is a number, not a vector. Right? It's the slope of the tangent line. Remember, a slope, rise over run, is a number. There's no direction with it, right? You need to pick out a direction to calculate the directional derivative, but the directional derivative is just the value of the slope of the tangent line that you get in that direction. It's the rate of change of the function in a particular direction. Okay? But the gradient, however, right, that is a vector, not a scalar. So don't get those mixed up, right? Yeah. Yeah. Again, if I have a better picture here, let's suppose this is my xy plane, and I have some surface sitting above that. Well, so let's suppose my surface just looks like this. Yeah, let's do little contours here if it helps. Right. So the directional derivative at a specific point, let's use this point right here. So this is my x0, y0. And I want to calculate the directional derivative in the direction of u of some function. Again, this is the function here. This is the graph of the function. It's a surface. Right, so this is a number. Right, now I have to pick out a direction. Let's say I pick out this direction here. That's my u. Then I go up to the graph here, to the surface, and I draw a line. I just lift this up to the surface here, and I draw the following curve passing through, right, that point on the surface. And then I take the slope of the tangent line to that curve, right? And that's what gives me my directional derivative, right? So it's the slope of this blue line. Right, so it has a rise and a run. So rise over run. Okay, so I hope that picture helps a little bit, right? The directional derivative is not a vector, it's a scalar. If you write it as a vector, it's automatically wrong. And the gradient is a vector. If you write it as a scalar, that's also wrong as well, right? So when we did this example up here, right, if you're not careful and you write the gradient of f at negative 5, 7 is 18 plus 22, right, which would be 40, that's absurd. The gradient is a vector. There's a little arrow over it. 40 is not a vector. It's a scalar. So you cannot have a vector equaling a scalar. Okay, so please don't make that mistake. Gradients are always vectors. Directional derivatives are always scalars. Okay, so now we come to another property of the gradient. We have a function f differentiable at a point. And the first thing it says is that if the gradient is the zero vector, and we actually saw an example of that already, the gradient, right, it is a vector, but at a specific point, it could be the zero vector, right? And if that's the case, then the directional derivative of any function f in that direction has to be 0, right? Not as a vector. Remember, directional derivative, this d here means directional derivative, right, is a scalar. Okay. So let's prove that, because it's a very simple proof. Remember, the directional derivative of a function f in the direction of u is just the gradient of f, right, dot product with u. But we're assuming that the gradient is the vector 0. So if I take the vector 0 and take the dot product with any vector u, right? I mean, u happens to be a unit vector, but it doesn't matter, right? 0 dot any vector is just 0 as a scalar. And that is the directional derivative then, right? So it doesn't matter what direction you look at, right? It doesn't matter what u is. If the gradient is 0, the directional derivative will always be 0. Okay, and let's take a moment to think about that. How can that happen, where the directional derivative is the same in every direction? So yeah, so here's the picture. Suppose we have, again, our xy plane. And let's suppose the graph of this function z as a function of x and y looks like this, right? Looks just like a little mound here, like a little hill, right? Right. So suppose I take the peak of that hill, right, at the very top here. So project down to the xy plane, right? Let's suppose this is my x and y down here, right? And then, of course, this is the point xyz, So, right. So notice what happens if I take any direction here and I take a curve in that direction. What's the slope of the tangent line? Well, it's not going up, it's not going down, so it's 0. Right? If I take some other direction, let's say I take this direction here. So now the curve looks, going backwards, it looks more like this. Right? But now the slope is still 0. Right? So you can see what happens here. At the peak of the hill, let me get rid of all these things here. You're sitting at the top here, right? You're sitting at the very peak. Oh, I did too many arrows here. Sorry about that. Right. So if I were to take a little plane here and balance it, place that on top of that point right there, right, it doesn't matter what direction I'm looking at. All these tangent lines are not going up or down. They're flat, right? They're just level with this plane here. Okay. So if you're at a different point, say over here, then you have a positive slope, right? Your slope is going up in that direction. At a different point, you have a different slope, right? In a different direction too, by the way. But all these lines that I drew here, right, have slope 0. And so the directional derivative in any direction u, right, no matter what direction you pick, will always be 0. Make sense? Okay. Number 2. So there's a second part to this that says the direction of the maximum increase, right, the maximum increase in the function, right? So if you want to basically go up in the steepest direction, you go in the direction of the gradient. Okay, so let me draw a different graph here. So let's suppose this is my xy plane. Right, so this is for number 1, this is for number 2. Right. In fact, let's just, okay, this is going to be kind of hard to draw here, but let's take something like this. Right. So this is my surface. This is z as a function of x and y. Different points have different heights, right? Oops. So, right, so at a given point, say x0, y0, right, you go up to the surface and you hit your z, say right here, right? So this point is z0, which is f of x0, y0, right? So that's the height. This is z0 here. Well, as a point, it's right x0, y0, z0, let's say. So that's the point on the graph, right? Okay. So here's the question, right? What direction should I travel in? This direction, this direction, this direction, this direction, this direction, in order for me to go up the hill in the steepest way possible, right? So I'm a mountain climber. I want to go up the mountain, right? Not down, not just left and right, right? Not just skirt around the mountain. I want to go straight up. So what direction should that be in, right? So if I go in this direction, I'm not going up or down, right? So the directional derivative here would be about 0, right? And if I go this way, I'm going a little bit down, or a little bit up if I reverse it. If I go in this direction, again, I'm mostly going side to side. On the other hand, if I go up this way here, I'm going up the steepest way possible. So it looks like this direction here. Right. So it turns out that that vector down here, right, this, and maybe I'll use yellow here, this, if I can't mess it up, this little vector here, right, is actually the gradient, points in the direction of the gradient of the function. So the gradient picks out the one direction that takes you up the hill in the steepest way possible, the maximum increase in the function f. Okay. Now, number 3, so now they want the direction of the minimum increase. And so for that, you just go in the opposite direction, right? So here you just go this way, and now you're going straight down the hill in the steepest way possible, right? So this will be just a vector in the opposite direction. Okay, and that takes you down the hill, right? So the slope will be negative there, right? The slope will be negative. So why they call it the minimum increase, I don't know. I find it easier to remember this as the maximum decrease because it's not increasing, right? If you're going down the hill, well, sure, that I mean, on some level, that is the minimum increase, right? It's the way to increase f in the smallest way possible. But what you're really doing is you're going down the hill, right? You're decreasing your z values, and so you're decreasing the function. So I would call it the maximum decrease, not decreasing, the maximum decrease rather than the minimum increase. But I guess it's the same thing, just, but minimum increase does sort of, to me, imply that the directional derivative would be positive, right? Because if you're increasing, you're going up. And we're not going up, we're going down. So we're definitely decreasing, right? The maximum increase will be positive. The maximum decrease will be negative. The maximum decrease or the minimum increase, depending on how you look at it, will be negative, right? Yeah, so that's why there's a negative in front of the magnitude, right? So if you want the actual maximum increase, you just take the magnitude of the gradient at that point, and that'll be the slope of the line going up. So it'll be positive, right? So to make it negative, just put a negative sign in front, and then you're going down the hill, which would give you a negative value, which would make it negative. Okay, so the gradient, the important thing about 2 and 3 is that the gradient picks out the direction you want to go straight up the hill, right? And the negative of the gradient points you down the hill, right? So it points you down in the steepest way, but now going down instead of up. Okay, and in light of that, if you look at number 1 here, where the gradient was 0, right? Remember, when the gradient is the 0 vector, there is no direction, right? So all these vectors down here, I wish I hadn't drawn them. So these should be eliminated here. Hang on a second. Yep. So yeah, right below it here, all these lines come from this point here, and this is the 0 vector, right? There is no direction. There is no magnitude here. And that's why the directional derivative is 0 in all directions. Okay. So yes, there is no increase, there is no decrease. You're just flat. You're horizontal. Right. And so this is going to come up a little bit later when we talk about critical points. A critical point is where the gradient is 0. So that either gives you a peak, like this, or in some cases, a valley, right? So if this is pointing downward like this, you're at a minimum. So this is how we're going to find our maximum and minimum points on our graphs, right? Kind of like we did in Calc 1, except now it's a little more complicated because, right, it's a function of 2 variables instead of 1, but it's a similar idea. Right? Instead of setting the derivative equal to 0, you set the gradient equal to 0 to find your critical points, not just critical numbers now. Okay, so that's coming up shortly. Okay, a couple other things I want to point out here. You have your surface, right? F is a function of x and y, so this is the xy plane below it. I know it doesn't matter which one's x, which one's y. Here's x, here's y. Right. right, and then of course this is z, so this gives us the height at a given point. So if we just take a plane, let's say z equals 5 or whatever, right, and we just slice this surface at that point, what do we get, right? We get a curve, right, that's a section of the surface. And if you put that on the xy plane below, you might get this curve over here, close enough, right? And if you use a different height here, right, you might get a different curve. This one here, right? Or go a little bit below here. Let's say this z value here, z equals 3. Maybe this was z equals 7. Right? And so now you're going to get, let's say we get almost a circle here, right? Right. So these are the level curves, right? The isotherms, the equipotentials, or just the height of constant z, right? Constant height. Right. So let's flip this and look at just the xy plane and look at the level curves, right? So let's say all these level curves look something like this. It's kind of hard to draw here, right? I'll draw a bigger one. Okay, right, and so this might be, z equals 2, z equals 3. This curve might be z equals 4, and so on. So there's some sort of a peak here, right? Here's where you might have the peak, the highest point. So this might be, z equals 10, the highest point. Right. So if you're going to draw these level curves, the gradient at a given point, right, as a vector, excuse me, these will be normal, that is perpendicular, right, to the level curve at that point. Right. So in other words, if this right here is my x0, y0, right there, the gradient has to point perpendicular to the curve. Except I think I got it backwards. It's pointing inward. It's pointing this way, right? But still perpendicular. Right? At this point, it would be pointing this way. Right? At this point, it would be pointing this way. Now, I don't know what the magnitude is. The magnitude also depends on the slope, the steepness, right? Right. At this point, it'd be pointing this way. Here, it's pointing this way. On this one, it's pointing this way. So at any given point, all your gradient vectors have to point right normal to the curve. Right? So why is that? Well, remember, if you're on a level curve here, let's say z equals 5 here, say at this point right here, right, on the surface. So which direction do I want to go if I want to go in the steepest direction possible? If I want to go straight up the hill, I want to go in this direction, right? Because if I go in any other direction, if I go in this direction, I'm just going around the hill, not up or down, right? I'm just basically going along the level curve. So if you're moving along the level curve, around the mountain, you're not going up or down, right? So yeah, you don't want that direction. You want to go up the steepest way possible. And if you're on the other side of the mountain, if you're over here, right, if you're standing right there, which is right above this point here, and you want to go straight up the mountain and the maximum increase, you want to go up this way. So the gradient would point this way. Okay, so these are the gradients down here. Okay? Right. These vectors here are not gradients. Right? Not in this case. The gradients are the vectors in the xy plane. Okay, so here's another example. All right. Suppose the function, let's just make it simple. How about x squared plus 2y squared? Right. What's the gradient? So it's a vector with components that are partial derivatives. So this is just the definition of the gradient. So the partial of f with respect to x is 2x, right, times I, plus the partial of f with respect to y, so you would get 4y times j. Just to emphasize, right, this is a vector at a given point. If I plug in a specific point now, let's say I want to take the gradient at the point 3, 4. Then I plug in x equals 3 and y equals 4. And I get the vector 6, 16, right? Or 6i plus 16j. Okay. So notice that this is a vector with only two components, right? There is no k here. Right? If you like, k is, right, 0 times k. But there is no k. It's a vector in a plane. Okay. So when I said earlier that the gradient picks out the direction, here's the gradient, picks out the direction in which you want to travel to go up the mountain, right? The gradient doesn't point up the mountain. It points in the xy plane, right? Basically in the map here, right? So if you're standing on the level curve right here, right? And this is a map, and you want to go up the mountain, what direction should you go in? You should go roughly in this direction. That still doesn't look right, right? You want to go in this direction, right? Perpendicular. Right. On the other hand, if you're at this point right here, you want to travel in this direction. But what it does not tell you is, right, how steep you're going, right? For that, you get the magnitude of the vector, right? If the magnitude of the vector is much bigger, that means it's much steeper, right? If the magnitude is less, then it's not very steep at all. Okay. So in fact, the closer that the level curves are to each other, right, the bigger the gradient, right? So these are pretty steep here, whereas over here, yep, these are a little bit less. They still point perpendicular to the curve, but we know that the gradient, the magnitude of the gradient will be a little bit less because it'll be less steep there. I hope that helps, right? So the gradient points in the direction in the xy plane, right? It's not a vector in space. Right. Unless you have an example like this. Let's suppose g is a function of x, y, and z. Right? And let's just make it x, y, z. Right. Now remember, this is not a surface in space anymore. Right? This is a three-dimensional volume in four-dimensional space. So I can't graph that. We're not going to graph this, right? Right. This is essentially a scalar field. Every point in space, field, has a different value. Right. So for example, if I pick the point in space 3, 4, 2, what's the temperature there? What's the value? It's going to be 24, right? 24 whatever degrees, right? So that's the value at that point in space. But I can still ask the question, in what direction, right? In what direction is G increasing the maximum, right? Is the maximum increase in G? Right. And let's say at the point, right, 3, 4, 2. Oops, that should be a 4. All right, at the point 3, 4, 2. Right, so what is that direction? Well, it's still the gradient, right? So we still have to calculate the gradient of G. However, this is a function of 3 variables. Right? This gradient will have 3 components. It's going to be the partial of G with respect to x. That'll be the x component. And then the y component will be the partial of G with respect to y. Right? In the j direction. Right? But it also has a z partial derivative. And that'll be the z component. So this vector does have 3 components. And so to answer the question, in what direction is the maximum increase? Well, now I just take my gradient as a function of x, y, and z and plug in 3, 4, and 2. Sorry. Plug in 3, 4, and 2. Right. Oh, we never took the partial derivatives. What are the partial derivatives? Sorry about that. So what is this going to be here? So the partial with respect to x, right, here's the function, is just y times z. So y times z times I. And then with respect to y, the partial derivative will be x times z in the j direction. And then the z partial derivative will be x times y in the k direction. Right? Okay, so that's the gradient as a vector in space now. And when we plug in 3, 4, and 2, so at the point 3, 4, 2, what do we get? We get 8 times I, right? 4 times 2 is 8, right? And then plus x times z is 6, and then plus x times y is 12. Right? So now we get a vector in space, 8, 6, 12. Right? So in that direction, whatever direction that's facing, G will increase the maximum. Okay, so suppose this scalar field, let's suppose it represents temperature, because that's an easy thing to wrap your head around, right? We all understand temperature, right? And let's just say we're in a room where the temperature varies wildly, right? Some parts of the room are cold, some parts of the room are very warm, other parts are kind of, moderate in the middle, and some parts are really hot. If I'm at a specific location in the room, right, and let's suppose I crave heat, right? I want it to be as hot as possible. What direction should I travel in if I want to go in the direction where the increase in temperature will be the maximum? This vector will tell you that. That vector tells you what direction to fly in. You want to fly in that direction, right? Because now we're in space, right? We're not just on a plane. You got to fly in that direction to give you the biggest increase in the temperature. And what will be the increase in temperature? What will be the magnitude of that increase? Take the gradient, the magnitude of the gradient. Right, so that's going to be the square root of, let me get rid of this dot here. Right, the magnitude of this vector, 8 squared plus 6 squared plus 12 squared. So it's going to be some very big square root. Yeah, I should need a calculator for this. This is 64 plus 36 plus 144. So yeah, so you get 100 plus 144, you get 244. Okay. Which is 2 squared is 61. Oops. Which is approximately, 2 squared is 61, or about 15.62. Okay. So what is this, right? This is the maximum directional derivative of the function g, right, at the point 3, 4, 2, right? Yep, that's it. That's the maximum directional derivative of that function at that point, right? And what direction should you go in, right? That's going to be the gradient, right? In the direction v, right? In the direction v, sorry. In the direction of v, right, which has components, right, 8, 6, 12. Right. Now, that's not a unit vector, so if you want to make it a unit vector, divide by its magnitude, right? So you get 8 over 2 squared is 61. Oh, we can divide, right? So 4 over squared is 61. 3 over the square root of 61. And then 6 over the square root of 61. Right, so now we get a unit vector in that direction. Right? So instead of this yellow vector here, you get a unit vector with magnitude 1. So that picks out the direction if you want to increase your temperature the most. Okay? And if you want to decrease your temperature, if you want to go in the coldest direction, well, then just flip it around, right? Then take negative v, right? So negative 8, negative 6, negative 12. And if you go in that direction, you're going to end up in the coldest region. You're going to go in the maximum decrease of the temperature. Or the book would say the minimum increase in temperature, but, you know, if you're traveling in this direction, right, the rate of change of the temperature will be negative square root of 244. It'll be, right, because you're going in the direction in which the temperature is decreasing. You're going where it's colder, not warmer. Right? So yeah, when you reverse your direction, instead of going where it's hotter, you're going where it's colder. And so you get, you know, the maximum decrease in temperature. You know, right, again, the minimum increase is the way the book phrases it, but that implies that it's kind of an increase, and you're not increasing your temperature, you're decreasing your temperature. So I hope that helps. Yeah, so you can get a gradient, right, vector that has 3 components, but then it has to be a function of not just 2 variables, right? It has to be a function of 3 variables to get a vector, to get a gradient that has 3 components. If the function only has 2 variables, x and y, then the gradient will only have 2 components, right? The x component and the y component, or if you like, the I and j components. Okay? Yeah. So yeah, you can also take the directional derivative of a function of 3 variables. It's the same formula, of course. So if you want the directional derivative, I should use that color. If you want the directional derivative, right, of a function of 3 variables, right, you just take the gradient of that function, which will now be a vector in space rather than in the plane, dot product with u, which will also be a vector with 3 components, right? Right. So in other words, you just take the vector with the partial derivatives fx, fy, fz, dot product with u. Now, obviously here we can't use cosine theta, sine theta, because that's a vector in the plane. So that's not going to work here. We're simply going to write the components of u, right? u1, u2, u3. Right? So that's these numbers here, if you like. Right? So that will give you the directional derivative of a function of 3 variables as opposed to just a function of 2 variables. Okay? It's just a little bit more difficult to think about it. You have to think of it in terms of the scalar field, in terms of something like temperature, because you can't graph, like we did up here, you can't graph a surface in 3 dimensions, when you have a function of 3 variables, you would need 4 dimensions, as we talked about before. So I hope this helps, and I hope this makes it clear. And again, all the examples in the book are very similar to these: calculating directional derivatives in various directions, and then calculating the gradient, and then, make sure you understand the interpretation of the gradient as the direction of the maximum increase. And then the negative of that will be the direction of the maximum decrease or minimum increase, whatever. All right, so good enough.